Good morning. So we have discussed about nanomaterials, properties of the size dependent properties of nanomaterials, and synthesis, different types of synthesis of nanomaterials. That is, we have discussed chemical vapor condensation method, precipitation method, and also salt gel method. Now we'll see nanoscale materials. So nanoscale materials, we have fullerenes, carbon nanotubes, carbon nanowires, etc. So but here we are going to discuss about fullerenes. I think most of you know what fullerenes are. So fullerenes are a class of molecules which are made up of only carbon. So fullerenes means the first thing which comes in our mind is C60 or carbon 60. So carbon 60 is not only fullerene. So any compound which is made up of only carbon and which is molecular weight, that is C60 more than carbon 60, are called as fullerenes. It might be C60, C70, C68, 78, C80, all comes under category fullerenes. So in general, the most important fullerene is which is known as C60 because of its wide applications. So the fullerene or carbon 60 is also known as Buckminster fullerene. A fullerene is a molecule of carbon in the form of hollow sphere, ellipsoid, tube, and many other shapes. So, but it is mainly known of ellipsoid shape rather than tube and other shapes. So, spherical fullerenes are called as buckyballs and they resemble the ball, that is football shape. So, usually it is especially C60, carbon 60 is made up of hexagonal and it represents the football shape. So we also have cylindrical fullerenes which are called as carbon nanotubes and bucky tubes. So fullerenes are similar to structure in that of carbon, that is graphite, because it's made up of carbon only. It's composed of stacked graphenes sheets linked as I told you, hexagonal rings. So now let us see how these fullerenes are synthesized. So fullerenes are synthesized by vaporization of graphite at very high temperature, nearly 4000 degrees Celsius. So when you condense this vapors of graphite at inner temperature, that is in helium gas, what will happen? Mixture of various fullerenes we get. It might be C60, C68, C70, C80 in the form of carbon. So we're going to evaporate it get it. So the main product is carbon 60. So the extracted, we are going to extract it and crystallize using the benzene solvent. So the main ingredient to get our carbon, or that is fullerene, is nothing but our graphite. So graphite is going to hit it at 4000 degrees Celsius. So we get mixture of fullerenes. The main compound is carbon 60. We are going to extract it with what? Benzene, or extract with benzene and crystallize it. So let us see what are the the structure of fullerene. As I told you, the fullerene looks like football structure. The first one shows the football structure. The next one is chemical structure, the hexagonal. You can see the hexagon and it is connected, interlinked. The hexagons, many hexagons are interlinked to each other. Chemical structure of your fullerenes. So next, the 2D and 3D structures of our fullerene, that is carbon 60, especially carbon 60, 2D structure and 3D diagram. First one, hexagons are interlinked to each other. Second one is 2D diagram, it is football, exactly like our football. And third one is the 3D structure. So next, let us see what are the properties of our fullerenes. Especially we are focusing only about C60, but few properties are common for all fullerenes. So fullerenes are heat resistant and unique. So dissolve in common solvent at room temperature. In fullerenes, 12 pentagonal rings are necessary and sufficient to affect the cage closure. So fullerenes contain carbon atoms arranged as combination of 12 pentagonal rings and hexagonal rings. The chemical formulae of fullerene is C20 plus 2N. Actually, we have formulae for alkanes, alkenes and alkynes. So similarly, we have formulae for our fullerenes. It is carbon 20 plus 2N. The fullerene cages are about 7 to 15 Armstrong in diameter and are 1 carbon atom thick. So they are stable from chemical and physical points of view. That is, breaking the balls require very high temperature. Since why they are telling, I am telling stable, because if you want to bake the hexagonal bronze, you are supposed to supply the heat up to 1000 degrees Celsius. So they are high, they have very high tensile strength of any 2D known 2D structure or the element. Highest packing density of all known structures, impermeable to all elements under normal circumstances, even to a helium atom with energy of 5 electron volts. Now let us see the applications of fluorines. It is used in electrographic imaging, solar cells, non-linear, optical thin films, magneto-optical recording, etc. These are general applications of all fluorines, irrespective of carbon 60 or C78 or Si76, C80, etc. It is used in making carbon films, tunnel diodes, photolithography, and double layer capacitor and storage devices. It is widely used for conversion of diamond. So diamond, you know diamond, right? It is in the separation of chromatographic materials, absorbent for gases. It is used in gas sensors, temperature sensor, particle sensors, and reduction of organic vapors. Used as a lubricant, adhesive, not adhesive like Fevicol, charge transfer complexes, cosmetics, catalysts, etc. It's used in secondary batteries. What are secondary batteries? That is rechargeable batteries, non-aqueous batteries without what do you mean by non-aqueous batteries? Without electrolyte. So electrolyte is not liquid, right? And fuel cell electrodes. Other applications are, so it is used as a water soluble derivative of a fluorine. It will prevent HIV-1 protease enzyme. So and therefore it is useful in fighting against HIV, where there is one of the fluorine, that is fluorine 60, F60, C60. It will fight against the what? HIV virus. It's not a medicine. It can fight against HIV virus. I'm telling you again, it is not medicine for virus. It can fight against the HIV virus that leads to AIDS. So elements can be bonded with C60R or further fluorines to create more diverse elements, including superconductors and insulators. So fluorines and the derivatives are also applied to coat materials on some chemical sensors such as quartz, crystal microbalance, and surface acoustic wave sensors. Surface acoustic in order to absorb. So whatever echo, sound will echo in order to absorb that, especially in the theaters, we are going to acoustics is used. So it is coated on the surface of the acoustic wave sensors. So these are the applications of the fluorines. So fluorines is not only carbon 60, but it is C60, C70 up to C80. It's made up of only carbon. So we have discussed what are fluorines, synthesis of fluorines, properties and applications of fluorines. Thank you.